I'll say a few words, but after that I expect that Shayan is going to say a little bit more about himself. So it's really great pleasure to have you here, Shayan. We started a long time ago. It was a project that we had in Netherlands. It started in Netherlands, and it was a project that Abdul and Shayan are supposed to work on it. The project was about 3D modeling of indoor for emergency response. And Abdul was the postdoc within the project. He was doing some space modeling, subdivision, and Shayan was more on the data collection side and data processing side. So the idea was that he creates from point clouds indoor environments. And Shayan visited us once here in Sydney, and he completed his PhD last year very successfully. And now I'm curious to see how he's progressing for 1 year without us. Shayan, the floor is yours.
Thank you, Sophie. That's nice of you. So, I explained briefly about the project. So, the project, the idea was that so when we collect the data from the buildings, so complex buildings like, for example, hospitals or let's say airport or train stations, how we can quickly generate a 3D model. It doesn't need to be very complex detailed model, but a model that, for example, we can use it for disaster management. So what are the important elements there? And so ITC was working on creating these 3D models, and at Delft with Abdu, they are working on creating the space subdivision, for example, for disaster management and evacuation. So the data was collected, for example, with mobile laser scanners like Zeprevo or this trolley, like pushing cart, or even a backpack. So also it can be with terrestrial laser scanner, but as you know, that is a slow. Then the data are mainly point cloud that we work with, but also you can use Kinect, for example, Kinect data. So that is RGB depth data, also images, for example, to detect more details. So that was the project that I did during my PhD, and successfully I got my PhD. Then let me share with you the work that I'm doing. So then during my postdoc, I continued this work with one of the industrial companies that were involved, and that is CGI from the Netherlands. So they were interested in using these algorithms for the project. And of course, they wanted to convert this to a product. But also, I was interested in doing further research. So we started doing some use cases with CGI. So the first one was, okay, let me first explain some motivation that why we are doing. Of course, probably you know, but as you know, manual modeling and editing of big data is very time-consuming, labor-intensive. Then the process of the scanning of built environment is recurrent. So regularly you have this big data, and we need a scalable solution to repeat the process. So to avoid too much human interaction. So then the question is, how can we facilitate the process by smart algorithms? So the data that we collected was collected by Zeprevo, and it was 300 million points, almost, from 3 floors of this VRR building. and you see the building has kind of complex shape, and it had a lot of glass surfaces on this curve. So this is why you see all these reflected points outside. So it was creating a lot of noise when you use mobile laser scan. And for a demo, I reconstructed the first floor of this building to test my algorithm. The method that I used for my PhD starts with, so you have the point cloud, it starts with planar segmentation. So this can be ransack or region growing to extract the surfaces, planar surfaces. And then from the surfaces, I create an adjacency graph. So this graph, in this graph, every segment is represented by a node, and the edges of the graph show the adjacency of those segments. Then we detect permanent structure. So these are wall, floor, ceiling, and this is by analyzing this graph, so exploiting the topology of the graph. And then from there, we separate the noise furniture, clutter, from the permanent structure like wall, floor, ceiling, and then we can reconstruct the main layout of the building. And then we add, for example, some of the furniture as obstacles. We add doors and, if necessary, windows also. So here is like the workflows. You see that we have point clouds, and this is how it looks like. For example, inside there are this furniture, and after creating adjacency graph and separating permanent structure from the furniture and clutter, then you see that those parts that are like furniture, they are removed, and we just keep permanent structure. So this is kind of algorithm that automate this process. And then from here, we need to do the modeling, so make like surface models. To do this step, there are several methods. So the method that I use is based on boundary representation of walls, and every wall is reconstructed volumetric. So it means that if you imagine that a wall has two surfaces, we don't reconstruct it as one surface. We reconstruct it as two surfaces because it's like a beam representation. And then, of course, because of gap and occlusion in the data, or for example, here you can see there is a lot of glass surfaces. So these surfaces are really sparse. So those in those places, for example, where the wall meets the floor, there is a lot of gap. So to fix those gaps, we extend these surfaces to each other. So walls are extended to each other. And also, they are extended to floor and ceiling. And because we have the semantic of these surfaces, we know that which objects are extended to each other. And from here, then we can like create the 3D model. After this step, there was one further step that we were creating the volumetric spaces. So this is boundary representation, but imagine, for example, for each room, we want a volumetric representation. And that is something that we did it based on enclosure of the space. So we were making sure that each one of these spaces are closed space in terms of geometry. And then Abdu was creating this volumetric space, and then he was also creating a space subdivision for like further applications like navigation. One thing that happens when from here we create the space, we do the space enclosure and we create those spaces. The difference then that can occur is that, for example, here you see inside the building there is a like a empty space. So when we create those enclosure-based spaces, it also creates here, and later we need to discard those spaces because they are not really a usable space. But in boundary representation, that doesn't happen. So this is the example. So you see, for example, the curve wall here is represented by this planar segment. So you see where these segments meet each other. There is a little bit like inaccuracy in the geometry that can be fixed by replacing, for example, a curved surface, but that is like further processing. So this building.
Shayan, about this curly wall, actually, how do you make the segments? Do you decide how big segments you want to have, or somehow can you control? For example, can you make the segments smaller so the curve is going to be represented better?
Yes, to some extent it's possible to control it. So it depends on what threshold we define for the distance of points to the surface. For example, when we are using region growing, every time it calculates the distance of the points to the surface to add more points to that segment. And if we consider that distance very large, so let's say if, for example, here I put below 10 centimeters because also the data was noisy. But if, for example, you put 1 meter, then of course it means you get a bigger surface, bigger segment here. And instead of having like the curve structure, we are generalizing the data to like bigger segments.
Yeah.
So for example, when the data is very noisy, I go with bigger numbers. But in most of the data that I work also with different laser scanners, I normally don't go more than 10 centimeters because the accuracy of these sensors are between 1 centimeter to 5 centimeters. So to further generalize it, I would like 10 centimeters threshold.
It looks much better than what you had for the fire and rescue, New South Wales Fire and Rescue building.
Yeah, this one looks better because I think because the quality, the data, that one was corrected with BLK, if I'm not wrong.
Yeah.
And the registration of some of the walls was not accurate. So sometimes we had inaccuracy in registration of some of the walls. So there were like 2-3 layers for one wall. So it was more difficult to generalize. But as you can see, this is also kind of like complex. It's difficult to say. For example, here we have this really huge space that connects everything. And then there are smaller rooms. And some of these, for example, you see here is open, but here is closed. This is probably because here the door was closed after scanning, so it is segmented as part of the wall. So there are, of course, this kind of inaccuracy when we are doing automatic modeling. But if we really want to make it like the real representation of the building, we should correct those cases. The main challenge here was these points that you see outside. So these happen when there is a lot of glass surfaces. So everything from inside is mirrored outside. This happens during the SLAM, during the mobile scanning, and because of that, the surface here was very sparse, and yeah, I was getting also some segments outside, but because those segments were not connected to like floor and ceiling, automatically they were filtered out.
And you have in the point cloud, from these reflected points, you have something like looks like a straight line on the previous slide. Where does it come from? Yeah, this one.
You mean this? These are
no, not the small one, but exactly this. Very long. Yeah, exactly where
ones.
the mouse goes through. Yeah.
Maybe this is a building in front of it. I'm not sure.
Okay.
Yeah, it can be like another building or another structure.
Yeah, probably yes. Yeah, because inside you don't have such a furniture that is really.
Yeah, that's correct.
Safe. Yeah. Okay. Good.
Yeah. So this work, the accuracy is above 80%. So that is in average for different cases that I worked on. And with accuracy of 80%, I mean how accurate we can separate permanent structure from furniture for modeling. And for example, for this floor, I subsampled the data because even one floor has more than 10 million points. So I subsample it to 2 centimeters point distancing. That's enough for this work. And for this amount of data, it takes less than 10 minutes to do this process. The manual work is decreased by 80%, which is really good. So in some of the steps, for example, here, the user should look at the data that there isn't like a big missing wall. And after reconstruction here, also the user should look if some of the rooms are not reconstructed correctly. So that is the manual work and visual inspection of the data. So now during my postdoc, I was so if you remember, I told you to move from this planar segments. So these are still point clouds. And when we want to create a model, surface model, there are different approach. Probably you know that from point clouds, we can now with very good accuracy, we can extract this segmentation, the semantic segmentation. So with deep learning, we can extract furniture, wall, floor. So we can have this semantic segmentation actually with accuracy more than 80%. But then the question is, can we do this part with deep learning? Can we do the modeling with using machine learning? And this is something that is still deep learning and machine learning is not really strong at, like doing be applied in for geometry modeling or in geometries. So that is the question that I'm trying to answer during my research. So to zoom in and see what does it mean. So for example, we get point clouds and then we okay, this circle precisely should be here on one step before. So for example, we have a room here. Imagine from the point cloud, it looks like this. And it doesn't look like this because this is another data, but as an example. So we have the point cloud, for example, from one room. And we want to create the model per room, so like such a model. And then when we create individual rooms, then because all of them geometrically are in correct place, then when we add them together, then we get the model for the whole building. That's the idea. But of course, it needs a little bit maybe further work to make sure that these rooms are also connected. For example, through the door, we can connect them. But this is kind of room-wise segmentation. The previous approach, this one is planar-wise, and it's based on the wall, but this is based on the room structure. So what I'm doing, for example, I get the point cloud from the room. In this point cloud, we know what are the permanent structure. For example, already with machine learning, we extracted those. So we select wall, floor, ceiling, and sometimes, for example, in this one also pillars. And you see, so for example, here in this corner, there are a lot of missing data. That is because here there were furniture and it was not a scan, or here the other side the same. So when we want to make a 3D model, this should be fixed. So from here to here, what I do the segmentation. This is again planar segmentation, and this time instead of extending these segments to their intersection, like what I did before, I extend everything to the bounding box of the data. So everything is extended to the bounding box of the data, and then these segments cut each other recursively. And this creates a cell decomposition. So for example, this wall can be decomposed to many faces by all the segments that go through it, intersect. And this creates a lot of faces like this one, also inside the room. Some faces are created. And then the reconstruction task comes to how we can select faces that belong to the room and the rest are invalid. So for example, if you look at this one, part of this green wall on the top, this shouldn't be there because there is this beam here. So it should have this shape. So we should remove some of these faces, those invalid faces. So this process is like a face selection process to keep the valid faces and discard the invalid ones. And when you do that, you get a model like this. And then you can just, after that, it's easy. You just merge those faces belonging to the same surface, and then you get a nice model. But then this face selection here is a complex task because simply you can say, okay, wherever there are points on faces, I select them as valid. But then these gaps cause that there are some faces that they don't have points or they have few points, but still they are part of the structure because they after extension they are created, but because of occlusion they don't have enough points. So that's not enough reason to select faces. And here is the step that I'm trying to use deep learning. So to do a lot of training on this data, and then it comes to like classification of valid and invalid to get valid faces. So this is work in progress. By the way, here also we of course we detect doors and stairs. I didn't explain in this presentation, but if you're interested, there is explanation in the paper, or you can just drop me on it. So there is one more use case. It's about agent-based simulation, but if you have question about this part, I can answer.
Which network do you use?
For this part, I'm using DGCNN. It's dynamic graph convolution neural network.
Hi, Cynthia. I'd like to ask a question. Shayan, hi, this is Cynthia from construction. Thanks for the presentation. I think up to here.
She's not a PhD student, Shayan. She's.
Yeah.
Yeah, I think the deep learning part is quite interesting, but I didn't get it. Which part you actually want the machine to do it? So basically, my question is to replace you do deep learning because you want to replace some manual processing. So if you do manual processing, how much trouble you would have? What kind of problem? So how machine learning has improved its efficiency or reduced the manual handling? I didn't really get that part.
So if you imagine when we create this cell decomposition, if we want to do it manually, we should have kind of a software that we can select these spaces that are created after cell decomposition and discard those and only keep those which are valid. And for this part, if let's say, for example, this is the dataset from Stanford S3 DIS that has like 300 rooms. And from this 300 rooms, we are doing this like cell decomposition. So we are creating a lot of faces and they get the label valid, invalid. So if we do the training on this large data, then the network should be able to do this task for us, like to say, this face is valid, this face is not valid. And so when we give a cell decomposition to the model, we feed it to the model, then we expect as output, we get faces with labels valid or invalid. And when we keep valid ones, then it gives us this model.
Okay, so is the cell decomposition happening before the segmentation, or that?
No, it happens after. So segmentation is here. This is segment. Yeah. So segmentation here is two segmentation. One is semantic segmentation that happens again with deep learning, and it gives us from point cloud. It gives us the label for point cloud, and that is semantic label that, for example, it says this is a wall or furniture, and then from there I do also a planar segmentation to make sure that all the points belonging to the same surface are segmented in one segment. So you see, then we get a very nice, clean planar segmentation. And after that, so to each one of these segments, we fit a, bounding box. Okay, so each one of these spaces are like bounding box of each segment. But imagine, for example, this is a small one here, the horizontal one. If you fit a bounding box to it, it's a very small one. But we extend this one to the bounding box of the data, so you see it cuts through the room. And other faces also cut this one. But then at the end, what is left from this surface is only this part of it. So the rest should be removed, should be discarded. And then this task from here to here should happen with deep learning, because if someone wants to do this manually or even correct it manually, it's too much work.
Sorry, I couldn't really understand why you do this after segmentation. You already segmented them. Then why do you have to do the cell decomposition? What's the purpose of doing that?
Well, segmentation, still you have points, yeah? So you just give the points to one segment the same number. It's
Yeah.
you still are working with points. But from points, you want to have a surface model, a 3D model like this one, for example. This is why we create faces.
Okay, so that means you actually put points together and then form an a plane.
We form a face, yeah. So it's a you can call it vector or a surface or a mesh, something like that. But it's a mesh. It's not really a mesh. So each one of these segments creates a polygon that probably has 5 or 4 or 5 vertices, most of the time 4. And then you are able to extend them together and create cell decomposition, because you cannot extend points to each other. So this is why it happens after segmentation. So this one looks like surface, but actually these are points. These are our like million of points.
What do you call it? Cell? Why it's cell decomposition? What do you call it?
Because here it creates a lot of small cells and like polyhedrons, polyhedra. So each polyhedron is a cell. So you have 2 options here. Either you can work with cells, so each cell can be very small or very large, and each room is decomposed to many cells, like 1,000 of them here, for example. Or you can work with faces of those polyhedron. So if you do face selection, you are reconstructing from the faces. If you work with cells and merge those cells to create the room, then it is cell decomposition. But in the terminology in research is cell decomposition. But actually, I'm working with the faces to select those cells.
Okay, so what kind of data you use to train your algorithm?
I'm trying to use S3 DIS dataset, because that is the dataset that has labels, has annotation. So I'm using that dataset.
Okay, I'm not familiar with that data set. So that's freely available. That's
yes, yeah, it's a famous indoor dataset from Stanford, and that's almost the only one that I know out there that is very large. There are a lot of deep learning models on it. Of course, for example, ISPR's indoor benchmark also there is data, but that is without labels. That one just has 3D models, has this one, but it doesn't have labels for points.
okay. So after this, the last picture, last figure you marked as primary 3D model. So that's after deep learning, you will get that 3D model.
Correct. Yeah.
Yeah. And then you stop here. I can see that it's still, well, to me, it's still not accurate enough to represent the walls compared to the real point clouds, because it has these windows or doors on it. So is that, you just stop here, or is there any further steps to?
This is why I call it primary 3D model, because of course you can continue like add more detail to this one. But the one step that for sure should happen is merging the faces. Well, you can also skip that. It's not really important, but you see, for example, this wall has 2 faces on it. You can just merge those to get one face, but that's not really necessary, because still these 2 faces are representing this wall. But if you want to, for example, here, if you want to add this door or this window, then you need to have two things. First, you need to have the points that are there. So then from those points, you can reconstruct the door, or at least know the location of the door. So that is something, again, for example, from deep learning model, you can have doors and windows. And then from those points, you reconstruct the object and you can add it. For example, you can add it with grammar, shape grammar, you can add it, or you can just use any geometry process to add details.
So your purpose is to automate this process. You use deep learning to make it easier to convert the point clouds to a 3D model. Is that right? That's your main purpose.
Yes. Yeah.
And the reason of doing that is when it turns into a 3D model, then it can be conveniently used for other purpose, where the point clouds obviously we can't use it directly.
Yeah, that's true, because so for example, if you look at this one, so the point cloud looks like this. So this is not really useful for any application unless you just open it and look at it. Like even if you clean it up, the only thing that you can do with it is like to look at it. If you want to do a query like how I can get from entrance to this room, or do a navigation, or how I can let's say select navigable spaces. This kind of things, when you want to work with, of course you can do it on point cloud also, but it means more processing. It means an expert that knows how to do it. But a 3D model like this, most of the softwares, 3D softwares, they can read these kind of models, and it's more useful. It's light in terms of size of the data. It's very lightweight. So.
So what kind of format it will stored? I mean, does it like the BIM modeling? So how do you store this 3D model? What kind of structure do you use?
These ones, I store them as any like geometry model, for example, OBJ format. But you can, of course, because they have semantic, for example, wall, floor, ceiling. So these surfaces, they have semantic. You can also store it, convert it to IFC format, and there you can create, for example, wall objects, door object, or ceiling.
Okay, sounds good. Yeah, but do you have to label them by yourself, manually? Like this is door, this is wall.
No, that's the whole process should be automatic. So that is the idea.
That's part of the deep learning process.
Well, here I'm not using deep learning, but I'm doing it automatically. So wall, floor, ceiling, door, stairs, all of them are labeled.
How could this happen automatically then from point cloud? That's just all points.
Yes.
How do they know this is door, this is window?
Well, I explained. So that's the process that, for example, I generate graph, I analyze that graph, and from that graph, I separate permanent structure from furniture. I can detect doors.
Okay.
So that's the whole process.
But that's manual processing to me.
No, it's not manual. Because if it is manual, then it's really excellent.
Hello. Hi, hello.
You use some criteria to separate which is door, which is window, which is wall. Yep. You have some internal criteria using the computer machine. I understand you use the machine to separate.
Well, I can show you on this image, for example. Okay. I know that you see this one, but it should be okay. So in this one, you see from point cloud, we create surfaces and we intersect these surfaces, and from here we create adjacency graph, and then here we exploit topology of the built environment to separate, for example, to know, okay, which node in each segment belongs to a wall, floor, and ceiling. So for example, one of these topology rules that you can exploit is that a ceiling is above a wall, and the relation is horizontal vertical. A floor is below a wall, and the relation again is horizontal vertical, and two walls are like almost vertical, and the relation is like vertical vertical. So for example, these are topology relation that we can find them in the data, and based on that we can give a label to those nodes, and each node of this graph represents a segment. So then we know that segment is wall, floor, and ceiling. Of course, during this process, for example, let's say if you look at a shelves, like bookshelves, they also represent the same topology. But if you follow from ceiling to the floor, then, for example, in case of shelves, this doesn't apply, this topology, because, for example, they are not connected to the ceiling.
Yeah. Yeah, I get it. So, you set up some criteria to identify each element and label them. Yeah.
But for example, for door, it's a totally different method. For door, we are using the trajectory, or for stairs, again, it's a different thing. So this adjacency graph is only for separation of permanent structure from the clutter and furniture.
Shayan, I think what Sincha means for when she say for her it's manual, it's because you are the one who decides the rules. Versus if you do machine learning, basically the machine is learning the rules through examples or through whatever data that you provide the machine, and then the machine will decide what is better. So if I'm not sure, but I think this is what I understood from what Sincha is saying. Of course, it's when you are saying automatic, it's because you are not you put your rule and you let the machine do the job, right?
Yeah.
It's right, yeah. But when she say it's manual, it's because you define the rule. So that's my understanding of what Sinja is saying. I'm not sure.
Yeah, that's true. Yeah, so it's the computer will do that. You set up some rules, and then the machine learning part is different. Then you have to train. You start to train it. So that's two ways you do these two different things. Yeah. That's fine. Yeah. I just try to understand what you do.
Exactly. Yeah, that's correct. So, well, in machine learning, also, if you select those features yourself, not with deep learning, then it's more or less like this method. So, if you decide on the features, for example, planarity, curvature, eigenvalues, if you select those features, for example, for random forest or to train a support vector machine, then still an expert is deciding what features best fit the machine learning algorithm. But of course, in deep learning, if you have a lot of labeled data, you can let machine decide for you. But that's the problem with deep learning, that if you don't have labeled data, then you cannot really use it. So, for example, in this case, and the other problem is it's not general. You cannot generalize it from one data set to the other one. I mean, you can, but it's not really easy. So let's say, for example, here I can use, of course, deep learning training on S3 DIS. But then if I want to use it on this data set, I can guarantee that I even don't get close to 50% accuracy. So that's the decision of the expert how to approach the problem based on the data that is available and the complexity of the problem.
Yeah.
Okay, so I shortly present also this one. So this is the other work that I also presented at ISPR's conference last month. So this was with In-Control Simulation Solutions. That's a company that they are doing agent-based simulation for example, pedestrian dynamics and with CGI. So the motivation of this one was that so this simulation softwares to do the simulation, for example, inside the buildings, they need the 3D model of the building. But what I understood normally, they get from their clients' floor plans that they are not up to date and they are very difficult to convert it to a 3D model. Or if they get BIM models, they are lucky and get BIM models. Again, maybe the BIM model is not up to date, or if it is up to date, it's like overkill for such a problem because BIM model has a lot of details. But for simulation, you don't need those details. It's not necessary. So again, they put a lot of work to simplify BIM models to a simple model to create to use it in their software. So then we were thinking, okay, how we can, they were interested to our approach, and because scanning a building is very quick, but then they cannot use the point cloud inside their software or for simulation. So we decided to like do a project with them. So in this project, we identify important elements for agent-based simulation, and then we reconstruct those elements from point cloud to be able to do the simulation. So on the right, so on the left, you see the building that it has 2 floors, and it is very cluttered with furniture and also the noise. And on the right, we created a 3D model. We added obstacles, so some furniture as obstacles and doors to be able to do agent-based simulation. So for the reconstruction, I use the same method that I explained to you. So the same method that I use on the other building, and so what we decided to keep is wall, floor, ceiling. That of course they give the main layout of the building. Then we have stairs because we want to do like multi-story navigation or evacuation, and then we need some of the furniture to create obstacles to be able to plan the navigation for agents. And then we need also doors to connect the spaces when the agents want to move from one space to another or to evacuate the building. So here you see the first floor and second floor. Red ones are obstacles that are some of the furniture, and blue ones are the location of the doors. Then so then they were able to import this in their 3D model in their simulation software. There we defined a number of agents, for example, 20 agents, and then we locate these agents in different parts of the building. And also you can define, for example, gender, age, size for these agents. Yeah, then you run the simulation. So for example, what you see here, we did two simulation scenarios, one evacuation, one social distancing. On the left, you see this is for evacuation. So what is happening, the agents that are placed in different location of the building, they should get to the exit, which is here, and then gather somewhere here. That is the task that is given to agents. And then the time that this happens is recorded. This is really useful for so some of the clients, for example, like train stations or airports or a stadium, they really need this to be able to see where are the bottlenecks in the building, and if calamity happens, how they can avoid incidents. So for example, here you see purple area, it shows that there is a higher density, for example, this door and this corridor. So you see, of course, agents don't use this space to get out, because, for example, from this side also you can get out, but they use the shortest path, and that goes through here, and it shows that there are only two doors, and these two doors are like bottleneck, because here the purple area, all the agents wait there. And on the right side is about social distancing. So we place different number of agents in different part of the building, and then they move a little. You can also give them a task, for example, go to reception desk, do something, or go to coffee machine, gather there for 10 minutes. So you can assign different tasks to them. And when we do this, you see that because of the amount of space that is available, these agents are violating social distancing. They cannot keep social distancing. And again, the purple areas is showing this. So this is the 3D screenshot. So here you see there is time. So this is for evacuation. We can see that agents are gathered here, and time passes how many can manage to get out of the building. And this is for social distancing. So you see that there is a disc that shows this 1.5 meter distance for each agent. And if this disc gets red, it means the distance is violated. Also, you can define the distance of these agents to obstacles, so then they don't bump into obstacles. So then for navigation, we use like shortest path navigation, and here you see that medial access network is created to do the navigation. And here the video. So this is the point cloud. This building had something around 30 rooms. So you see here we have stairs. Also, they use the stairs to get from second floor to the first floor or ground floor. So you see here they are waiting to get out of this door. And the interesting thing of this simulation is that you can have like, so we did this with 10, 20, and 50 agents, and then we can see how is the time passing for example, evacuation, or in case of social distancing, when number of agents are increased and the time is increased, so how the social distancing is violated. So you can, for example, plan the capacity of the building. Yeah, that was my presentation. I hope you like it. If you have questions, I'm happy to answer.
Thank you very much. Yeah, it's really kind of, very interesting. And now we have time for questions. You showed to us a lot of things. Probably it could have been even two presentations. One on the 3D reconstruction and one on the edge-based navigation.
Hey, Shayan, thanks
because
for that.
I get. Huh?
Thanks for that, Shayan. I've just got a question. Is this on GitHub or are these routines accessible?
You mean the code, the algorithm?
Yes. Yep.
The one from the first work, we put it, so this one, we put it on GitHub, but then later we removed it because we decided with CGI, we decided to like change and like make kind of product from it. So now it's not on GitHub anymore.
Right. Yeah. Okay. No, nice work. Great presentation. Thanks.
You're welcome.
Questions for any of the two parts of the presentation? I want to go to this slide, Shayan, that you are explaining to Cynthia about slide 8, about deep learning.
Mm-hmm.
Actually, you said something that I was kind of puzzled. You say first that you make a segment. From the segments, you get something volumetric, which is the bounding box of the segments.
Mm-hmm.
But after that, you said that you are using the planes. So which of the two?
Well, segments are planes.
So you're fitting a plane to the segments. You're not making the minimum and maximum bounding box.
Well, fitting a plane, I fit a plane to the points, and that gives me a segment.
Yeah,
and then
okay.
from that segment, so for example, let's say these points are now one segment, and then they belong to the same plane. And then from this segment, I create a bounding box that is a face, a rectangle, simply 4 vertices.
Yeah, okay. Yeah, I get what you want, what you mean with bounding box. You mean the you get the outer boundary of the segments.
Yes. So for example, if you look at this, if I want to connect these corners, it gives me a polygon like this one.
Yeah.
But then it doesn't represent this part of the wall which exists, but there is no pointer. This is why we create a bounding box. But again, the bounding box is not enough because it's so for example, if this wall, let's say if we don't have
so
also
it's
this
bounding box, but it is in the plane. It's not volumetric bounding box.
No, it's just a plain bounding box.
Okay.
Here is volumetric bounding box. This has a thickness, so it's a really box. But this one is this box and is a little bit confusing. That has so better to say like a rectangle or a
Yeah,
face.
better to say rectangle indeed. Yeah.
And but still we need to extend all of those to the bounding box. This time is a real bounding box of the data. We extend it to that one, because if we don't do that, then imagine if this part of the data is missing, then it's not representing that part of the one.
Yeah. And actually, that's why you are getting this hanging or overshots and from all the sides of this room.
Exactly, yeah.
Yeah. And you have to remove them, yeah.
I have one question.
Yeah, go ahead, Hershey.
Yeah, hello, Shayan. Nice.
Hello.
It was a very nice presentation. I just have one question that, sorry. Can this adjacency graph will be useful for exterior point clouds or just for the indoors one?
That's a good question. Well, of course, you can use the graph for any types of problem. Because, for example, here also there is a graph network. So you can create a graph from your data, but that depends on you what you want to do with that graph. So you can create adjacency graph. For example, they create different type of graph like superpoint graph or for graph cut problems to do this semantic segmentation. But then, so from here, then you need a different approach to process that graph.
Okay. So actually, so I was example, working with outside.
You can cluster some of the points. So if it is outdoor, also you can do planar, or you can just do like k nearest neighbor. You can cluster them, and each cluster is represented by a node in the graph. And then if they are adjacent, there is an edge.
Okay, so the basic idea of adjacency graph is like all the objects that are adjacent to each other. So just creating the relation between them, something like that.
Yes. Yeah. So what this DigitCNN is doing that I'm using, it gets k nearest neighbor, for example, 20, and then from those nearest neighbor, it creates graph, and then it uses graph convolution on this graph to train the model.
Okay. Can you just, in a basic idea, you can explain the concept of adjacency graph that you explained earlier also, I guess. Can you just give me a bit?
So if you look at this one,
yes.
So this is, so here, for example, if you look at this part, you see there are several segments. Each segment is represented by a node. And when they are adjacent, like, so adjacency also, it's how you define adjacent. It can be based on the distance, or it can be semantically they are like connected. And then if they are connected or adjacent, you connect them, these nodes in the graph. And then each node get the properties of that segment. This can be if it is vertical or horizontal, like what is the size, can have many properties, each node. And then the edge gets the type of the relation. So for example, the distance,
topological relations also.
Topology relation, etc. In the paper, I explain more in detail.
Okay, sure. Thank you, Sean. Very good presentation. Really like it.
Okay, some more questions?
Yes, I have one.
You want
No,
to?
no, it's
Go
a
easy,
serious,
go
Want
it's
to
a
easy.
give
serious
him
Be
now a
kind,
hard
be
time.
No, not at
Abdul,
all.
okay, go
Not
ahead.
at all. This is really, I'm really coming with a positive mind. So in the 3D, how do you call it? The last model that you get, the 3D model.
Mhm.
How is it in terms of, yeah, the primary 3D model? How is it in terms of water tightness? I mean, did you see some kind of improvement? Because one of our struggle was to get something watertight out of the. And did you see some improvement in that aspect, like using deep learning?
So this happens before deep learning, the water tightness, because you are extending everything to each other, correct? And to the
Yeah.
bounding box of the data. So
Okay.
so it
Everything
actually,
intersects.
yeah, everything is
Everything intersect.
intersect. Yeah. So so it guarantees water tightness unless there is like imprecision in the geometry.
Yeah.
That, you know, for example, in SIGAL it happens sometimes.
So then it will be at the cost of precision of the model itself, like the fact that you extend everything, you get something watertight, but somehow you change more or less the shape of the structures in the model itself.
Yeah. Then what do you mean you change the shape of the structure?
Oh, you have to get
I
the
mean,
same shape.
yeah, but if you extend everything and you cut and you, let's say, all this plane you are extending. So, but for example, if there are some kind of small stuff on the wall, obviously you will lose those details.
That depends how
How
much you
segment.
want to generalize and how you segment. So, for example, let's say this
Yeah,
frame that is
yeah.
on the wall. If when I fit a plane to this wall, if I segment the points from that frame with the wall, then I'm generalizing there a little. But let's say if there is kind of very small structure, like a part of a beam or a pillar in the wall, those you can reconstruct. So as long as your segmentation, your planar segmentation is accurate and the selection of the faces are accurate, the reconstruction can happen accurately, and it's also not Manhattan. So it can cover all types of structure.
Yeah, yeah, that's right. But probably one I haven't explored at all this machine learning, deep learning area, but maybe I'm not sure. Maybe you can tell from your experience. But probably an area that it can help, and where humans are struggling, is to choose threshold, proper threshold for this kind of issue. Because right now you are mentioning about segmenting, but how do you decide the right amount of a segment, the right size of a segment? How can you, it's a threshold obviously that you have to set yourself. So do you think deep learning that you are exploring can help in that issue? If Shayan is still around, yeah.
Yeah. Sorry, I was sending a message to the work because I should leave in some minutes. So
yeah, I will give you some few more minutes just to make
so
sure.
you mean the threshold of the when we do the planar segmentation?
Yeah,
That
for
threshold.
example, yeah.
I think you can also replace that with, again, training, if because there is some methods for, like, to train for ransack, for example, but they are not really successful. You can replace that, but of course you need a lot of training data and you don't want to go there because it's just one threshold. The way that I decide is based on the points distancing. So how much you subsample your data. For example, if you are subsampling to 5 centimeters point distancing, okay, that is very sparse, but then you cannot fit a threshold less than that, okay? And if your data, let's say you collected with a terrestrial laser scanner that gives you accuracy of 3 millimeters and point distancing of less than a centimeter, you don't go with 10 centimeter threshold because that's overkilling for such an accurate data. You go for, I don't know, 3 centimeters, for example, because that gives very, very clean planes. So that's a little bit also like unsupervised way to do it, and with like practice, trial and error.
Okay. Good, thank you. Very nice presentation. Surprisingly, but
Yeah, I think it's quite interesting too. Mudan, you're there. I think, yeah, Cici, you know, Mudan's thesis also look at the choice of parameters and the thresholds. Yeah, so I think that's quite inspiring. Yeah, Mudan, what do you think? I think that's related to your research as well, because you've been trying to determine what's the best threshold when you're with the segmentation and plane fitting.
But in his studies, he used the subsampling about the point cloud, but I didn't do that. So the point density or the distance among the points are not very are not average. So the threshold setting of the plane segmentation could be a little difficult because we don't know we can't because I didn't do the subsampling about the point cloud data.
Well, you can. I can also like avoid subsampling, but then it means longer time of processing, which is not necessary because I reach the same accuracy if I do subsampling, but in a shorter time. So, but for example, if you want to use deep learning, then you don't do subsampling because you want more data for deep learning. So you keep all of your data.
Yes, because I want to do the quality check of the prefabricated element on the construction site. So I don't know if I do the subsampling, it could reduce the accuracy because I need to do the quality check.
And what accuracy you're looking for? Like, I think in construction it is around centimeter, 2-3 centimeters, maybe. Yes.
Now the requirement of the quality is about 5 millimeter.
Okay, so it's below centimeter. Yeah, and the data normally is with terrestrial laser scanners. Yes.
Yes. Yeah. Yeah.
Yeah, for those accurate construction applications, yeah, better to keep the data as accurate as it is.
So it can be done that just manually keep trying the parameters. Mudan, that's what you've been doing. So you just choose range of numbers manually and then try it to see which one will give you the best segmentation. But
yes,
then instead of doing that, you could introduce machine learning to detect what's the best value.
Yes, maybe I can try it using deep learning for the segmentation. Do you think, Cici?
At the moment,
I don't know.
Yeah, I don't know how much time to spend on.
To specifically for the thresholding to go to a machine learning, and especially for construction sites. Every floor, although it's the same kind of layout, they're different because you have so many different things happening during the construction. So I don't know how are you going to train it. What kind of data you are going to use to train? And this only for one threshold.
It looks like, but I don't feel that you spent a whole lot of time to get the correct or suitable parameters for the case we studied. But what I was thinking, if every time we change the setting, if the prefabrication are happening on different design things, and you have to choose another parameters to the segmentation, then that makes sense if we can use some automated method. But if we try different, most of the sites can use similar parameters, then we don't have to do that. But I don't know how much difference that will cause. If the layout, if the design changes, then do we have to change those parameters significantly, or it's just a small variation? We could manually try a few times, then we'll get accurate number, and that's good enough. I mean, that's in terms of practical value. But okay, anyway, maybe we should have a think, afterwards. Yeah,
well, deep learning can be always a solution, but the biggest problem of it is always you need a lot of data. Otherwise,
the training data, that's true.
Otherwise, it doesn't turn out good. And I
you
think
have
for
to
the
have
work,
similar data to what you are trying to solve.
well, for example, for the work that Mudon is doing, it's really like specific to construction applications. So unless you want to get the semantic of some of the structure, for the rest, I don't think deep learning helps. So you can just use deep learning to know what is the classification of the data. And well, in construction again, I don't know what are the classes, debris sometimes. But yeah, that's the different application. So you should prepare your own data.
Anyway,
okay.
I think
if you let me, I should.
I think it's quite inspiring, your presentation.
I should leave.
Okay, so thank you very much, Shayan.
You're welcome.
Very nice seeing you again. And when you have some results, you can come again and show something to us.
So you have this workshop every month?
Twice per month.
Okay. Nice.
So.
Okay. Thank you for inviting me and giving me the time to present my work. It was really good to see you all again. And we keep in touch.
Thanks, Shayan. That was a fantastic presentation and a good discussion. Thank you.
Thank you. Goodbye.
Bye-bye.
Thank you. Thank you. Bye-bye.
Bye.
You can send him mail. Bye-bye, everybody.
Bye.
Bye, everyone.